All right, get ready, because today we're going deep
Wait.
into the world of transformers.
Ooh, transformers.
But not the Optimus Prime kind.
Yeah.
The AI kind.
Yeah, the ones behind all those powerful language models, like
Like GPT-3.
GPT-3, yeah.
That seem to be, like, everywhere these days.
Everywhere you look.
Have you ever wondered how these things actually work?
Under the hood?
Yeah, we're going to unpack some really cutting-edge research
Fascinating stuff.
from Anthropic
Yeah.
that breaks down these complex models.
They can be pretty dense.
Yeah.
But this research makes it surprisingly understandable.
Yeah, in a really cool way.
Yeah, and what's so interesting about this research is it takes a different approach to understanding these models.
Okay.
A lot of times we describe AI in terms of, like, computational efficiency,
Right.
and that can be pretty dense and not very intuitive.
Okay.
It's like trying to understand a city just by looking at traffic patterns.
Mm-hmm.
You get some information, but you miss the underlying structure.
I see. So we're going deeper than that.
Much deeper.
Okay, so we're looking under the hood to see what makes these AI engines tick
Precisely.
and to make things even easier to digest.
Yeah, they had a great strategy.
The researchers focused on toy transformers,
Love that term, toy transformers.
simplified versions that still capture the core concepts.
It's brilliant, right?
Yeah.
You start small.
Yeah.
You can really grasp the fundamentals before you tackle the more complex models.
All right, so let's start with the simplest possible scenario,
Okay.
a zero-layer transformer.
0 layers.
What did that even look like?
All right, so imagine a transformer with no layers at all.
Okay.
It takes a single word or token,
Okay.
something like the,
Mm-hmm.
converts it into a numerical representation,
Okay.
and then immediately tries to predict the next word.
Okay.
It's essentially just relying on bigram statistics,
Hmm.
how often one word follows another.
So if it sees the word
The.
it's just guessing the most likely next word based on its training data.
Precise.
So very basic.
Very basic model.
Yeah.
But even in this simple form, it highlights a crucial element that's present in all transformers,
Okay.
the residual stream.
The residual stream. Okay.
Think of it as a communication channel
Mm-hmm.
that allows information to flow directly from one layer to the next,
Mm-hmm.
kind of like a shortcut.
So even with 0 layers, there's still this residual stream concept.
Exactly. We can imagine the token's numerical representation
Yeah.
flowing straight through this residual stream to the output.
Okay.
And it's important to note that the residual stream is linear,
Okay.
meaning information is just added together
Uh-huh.
without any fancy transformations along the way.
Got it. So let's add a layer
All right,
and see what happens.
let's do it.
What does a one-layer, attention-only transformer bring to the table?
Now things get a little more interesting.
Okay.
With a single attention layer, the model can finally look beyond the current word and consider previous words in the sequence. The researchers discovered that these models essentially function as a blend of bigram and skip-trigram models.
Skip-trigram.
Skip-trigrams.
You're going to have to explain that.
All right, picture a sequence like ABC.
Okay.
The model learns to predict C based not only on B,
Right.
the current word,
Uh-huh.
but also on A,
Hmm.
a previous word that it chooses to focus on.
Okay.
This ability to skip over intermediate words allows it to capture more complex patterns.
So instead of just knowing that the is often followed by cat,
The cat.
it might learn that the fluffy is often followed by cat.
Exactly. It's a step towards understanding context.
Right.
And to decipher how these skip trigrams are formed, the researchers used a clever trick called path expansion.
Path expansion. Okay, what's that all about?
So remember the residual stream?
Yes.
Path expansion basically maps out all the possible routes information can take through the model
Yeah.
from the input to the prediction.
Right.
In a one-layer model, there's the direct path through the residual stream, and then paths through the attention head.
So we're tracing the flow of information,
Yes,
like following a map of the model's inner workings.
precisely.
Uh,
And by analyzing the math behind each path,
okay.
the researchers could literally read off the skip trigrams the model had learned.
Wow, that's pretty neat. So each attention head contributes to specific skip trigrams.
Exactly.
But how does an attention head actually decide which words to pay attention to and then how to use that information?
That is a great question.
Yeah.
Here's where the real magic happens.
Okay.
Each attention head is made up of 2 key circuits,
Okay.
the QK circuit
Uh-huh.
and the OV circuit.
Through K and OV. Sounds a bit like a secret code.
It does, doesn't it?
Yeah.
So QK stands for query key,
Okay.
and it's responsible for figuring out which previous words are most relevant.
So which ones to pay attention to?
Exactly. Imagine each word having a key and a query.
Yeah.
The QK circuit compares these to calculate an attention score,
Hmm.
showing how closely each previous word relates to the current word.
So it's like a matching game, finding the words that fit best together.
Exactly, like a matchmaking system for words.
I like that.
So once the QK circuit has figured out the relevant words,
Yeah.
the OV circuit takes over.
OV.
OV stands for output value,
Okay.
and it determines how the attended words influence the prediction of the next word.
So QK decides who to listen to,
Right.
and OV decides what message to take from them.
You got it. It's a two-step process.
Okay.
First, identify the important information,
Uh-huh.
and then extract meaning from it.
This is making so much sense.
It is pretty elegant.
Yeah, by analyzing these QK and OV circuits,
Yeah.
the researchers could actually see which skip-trigrams the model had learned.
That's right. And what they found was pretty remarkable.
Okay, I'm dying to know, what kind of skip-trigrams did they find in these one-layer models?
One of the most surprising discoveries was how much these models rely on simple copying behavior. Many attention heads were dedicated to just copying tokens from earlier in the sequence
Okay.
to predict the next token.
So it's like a basic form of in-context learning,
Right.
where the model just remembers and repeats what it's seen before.
Exactly. It's not deep reasoning,
Yeah.
but it's a foundational element for more complex behavior.
Right.
For instance, one head learned to copy HTML escape sequences like N and BSP,
Okay.
while another focused on handling quirks of the tokenization process, copying parts of words that had been split up.
Hold on, the model is learning to work around limitations in its own input.
It is.
That's fascinating.
It is.
It's like it's developing its own internal logic to deal with the messiness of language.
It is, and that's just the beginning.
Okay.
They also found heads dedicated to Python code structure,
Okay.
recognizing common function arguments, matching brackets across different programming languages, and identifying common phrases.
So it's picking up on both low-level patterns and higher-level relationships between words. Pretty impressive for a one-layer model.
It is, but this analysis also revealed some interesting bugs. Sometimes the skip-trigram logic would lead to nonsensical predictions, highlighting the limitations of this approach. It's like those optical illusions that trick our brains into seeing things that aren't really there.
Yeah, those are always fun,
Yeah.
but maybe not so much in an AI model.
Right.
Speaking of leveling up,
Yes.
what happens when we move to a two-layer transformer?
Okay.
Does it just mean more skip-trigrams, or is something else going on?
With two-layer transformers, we enter the realm of true composition.
Okay.
It's not just about having more attention heads,
Okay.
but about those heads working together in more sophisticated ways.
Okay, so it's about quality over quantity.
Precisely.
How do these attention heads actually compose with each other?
There are three main types of composition,
Okay.
each with a distinct effect. Q composition,
Okay.
K composition, and V composition.
Those sound familiar. Do they relate to the query key and output value circuits we talked about earlier?
Absolutely. Q composition means the query of a second layer attention head is influenced by the output of a first layer head.
Okay.
K composition means the keys are influenced.
Gotcha.
And V composition means the values are influenced.
So each of these circuits can be modified by the output of a previous layer.
Exactly.
That opens up a lot of possibilities.
It does. And these different types of composition lead to very different outcomes.
Okay.
Q composition and K composition affect the attention pattern itself,
Okay.
determining which tokens the second layer head focuses on.
So they're controlling which words get heard, so to speak.
Right. Imagine one attention head specializes in identifying names
Okay.
and another in locations.
Yeah.
With Q composition, you could have a second layer head that only pays attention to locations
Okay.
when a name appears in the previous context.
Wow, that's powerful. The model is learning to ask more targeted questions
Yep.
based on what it already understands.
Exactly. This dynamic adjustment of attention is key for more sophisticated in-context learning.
That makes sense for Q and K composition.
Right.
But what about V composition?
Yeah.
What happens when the values are affected by a previous layer?
So V composition is a bit different.
Okay.
It doesn't change which tokens are attended to,
Right.
but modifies the information being passed between them.
Okay.
It's like changing the content of a message without altering who sent or received it.
So instead of just copying a token,
Yeah.
A V-composed head could combine information from multiple previous tokens?
Precisely. It allows for a more nuanced and selective transfer of information.
Okay.
To really see the magic of composition in action,
Yeah.
the researchers focus on a two-layer model
Okay.
where they discovered what they call induction heads.
Induction heads. Now that sounds intriguing. What makes them so special?
These heads are a prime example of how composition unlocks new levels of in-context learning.
Okay.
They rely heavily on K-composition, building on the results of a first-layer head with a very basic attention pattern.
Okay, so we have a first layer head doing something simple.
Yes.
What kind of pattern are we talking about?
This particular head mainly attends to the word right before the current one,
Okay.
and to a lesser extent, the word two positions back.
Okay.
It's a very localized attention pattern.
So a bit of a nearsighted attention head, only looking at its immediate neighbors.
That's a great way to put it. But the fascinating part is how second-layer induction heads utilize this simple pattern.
All right, you got my attention. How do they do it?
Through K-composition, these induction heads learn to identify tokens that have appeared before in a similar context.
Okay.
It's like they're saying, hey, I saw this word before when the previous word was X. If the current word is also X, maybe the same word is coming up again.
So they use the first layer head's simple pattern as a cue to identify potentially relevant words from earlier in the text.
Exactly. It's like they're piggybacking on the first layer's ability to track local context.
To build a more global understanding.
That's mind-blowing. It's not just copying anymore. It's a more sophisticated form of pattern recognition.
Yes. And to visualize this, the researchers analyzed the attention patterns of these induction heads
Okay.
on the first paragraph of Harry Potter.
Okay, now you have to tell me what they saw. Did the model learn to recognize Harry Potter?
They found that the induction heads would light up when they encountered names like Dursley or Potters.
Okay.
They'd attend back to previous instances of those names, suggesting they were learning to predict their recurrence based on context.
So they're not just recognizing names, but potentially anticipating how those names will be used in the story.
Exactly.
That's incredible. This is way beyond what the one-layer models were capable of.
It highlights how composition unlocks a whole new level of expressiveness.
Right.
It's like going from simple addition to multiplication,
Yeah.
suddenly opening up a much wider range of possibilities.
This is all so fascinating, but I have to ask.
What about those other two types of composition?
Right.
U composition and V composition.
Yeah.
Did the researchers find any interesting examples of those in this two-layer model?
That's a great question. In this particular model, K-composition was the star of the show,
Yeah,
especially with these induction heads.
right.
They did observe some Q and G composition,
Okay.
but it wasn't as prevalent or easy to interpret.
So maybe those other types play a bigger role in more complex models.
That's a good hypothesis.
Yeah,
It's important to remember that this is just one piece of the puzzle.
right.
We're still in the early stages of understanding how transformers work,
Uh-huh.
and there are undoubtedly many more surprises waiting to be discovered.
Okay, so we've seen how K composition can lead to these amazing induction heads.
Yes.
But what about V composition?
Okay.
Did the researchers say anything about how those types of heads behave?
They did observe some interesting behavior in V-composed heads,
Okay.
but it was more subtle and less directly tied to in-context learning. Remember, V-composition modifies the information being transferred,
Uh-huh.
not the attention pattern itself.
Right. It's about changing the message, not the messenger.
Exactly. They found that V-composed heads often acted as a sort of virtual attention head.
Virtual attention head. Okay.
Instead of attending to tokens directly,
Okay.
they would effectively combine the outputs of multiple previous attention heads
Okay.
before passing the result to the next layer.
So they're creating a new synthesized attention pattern based on the work of others.
That's a great analogy. It allows the model to integrate information from different sources in a more flexible way.
Okay, that makes sense. But did they find any specific examples of these virtual attention heads doing something meaningful?
Not in this particular two-layer model.
Correct.
It seems like virtual attention heads might become more important in larger models
Okay.
with more layers and more complex interactions.
So it's another piece of the puzzle that we'll need to explore further as we delve deeper into the world of transformers.
Exactly. And that's what makes this research so exciting. We're constantly uncovering new layers of complexity, new mechanisms that contribute to these models' incredible abilities.
This whole deep dive has been a real eye-opener.
It is fascinating stuff.
Yeah, we've gone from simple bigram models to sophisticated induction heads.
It's quite a journey.
Yeah, all by breaking down the transformer's inner workings step by step.
Step by step.
It's amazing to see how these seemingly simple mechanisms can lead to such complex behavior. It really makes you wonder what happens when we scale up to those massive real-world models
Right.
with hundreds of layers and billions of parameters.
It's a fascinating question. The researchers believe that this type of analysis,
Yeah.
focusing on information flow
Uh-huh.
and the composition of attention heads,
Right.
could be the key to understanding even those behemoth models.
So instead of getting lost in the sheer scale of these models,
Yeah.
we can zoom in on the fundamental principles
Fundamental principles.
driving their behavior
Exactly. It's like having a blueprint.
to navigate the intricate architecture of these AI systems.
And by understanding these principles,
Right.
we might be able to address some of the concerns.
The concerns about AI safety.
Yeah, about AI safety
Yeah.
and making sure that these models are aligned with human values.
Absolutely. If we can pinpoint how these models learn and reason,
Yeah,
we can better anticipate potential issues
right.
and steer their development in a more responsible direction.
It's like being a mechanic for the mind.
I love that analogy.
Yeah.
A mechanic for the mind.
Figuring out how all the gears and cogs work together.
And just like a skilled mechanic can diagnose problems and optimize performance,
Yeah.
we might be able to fine-tune these models to be more reliable and beneficial.
This research really highlights the importance of understanding AI.
It does.
Not just as a black box,
Yeah.
but as a complex system.
A complex system with its own internal logic.
Right, with its own internal logic.
It's a shift from mere observation to true comprehension. And with comprehension
Yes.
comes the power to shape the future of AI in a way that benefits all of humanity.
Well said.
This deep dive has taken us on quite a journey.
It has.
We've explored the fascinating world of transformers,
Yes.
uncovering the secrets of skip-trigrams,
Skip-trigram.
induction heads,
Induction heads.
and the power of composition.
The power of composition.
It's been a real mind-bending adventure.
It really has.
Who knew that math could be so captivating?
I know, right? And this is just the beginning as
Yeah.
researchers continue to delve deeper into the inner workings of these AI models.
Yeah.
We can expect even more groundbreaking discoveries in the years to come.
I, for one, can't wait to see what they uncover.
It's going to be exciting.
Yeah, it's an exciting time to be following the evolution of artificial intelligence.
Absolutely. And we'll be here to keep you informed every step of the way.
Awesome.
Until next time, keep those brains buzzing.
And remember, sometimes the most complex systems can be understood by starting with the simplest building blocks.
The simplest building blocks.
Happy exploring.